Number 24. A uniform circular disk of radius r begins with a mass big M. About an axis through the center of the disk and perpendicular to the plane of the disk, the moment of inertia is 1/2 mr squared. A hole is cut in the disk as shown in the diagram. In terms of the radius r and the mass m of the original disk, what's the moment of inertia of the resulting object about the axis shown? Okay, we have some irregularity here because normally in engineering physics you take in the first and second year in your college, or maybe in AP Physics C class and even the AP Physics 1, they give you the formula. I think there are about 6 of them. One that has a cylinder and that the z-axis passed through the center, or one that has disk like this, and there are some more like a sphere whose z-axis just passed through the center of the sphere. Well, this time we are kind of changing it by cutting out the whole of this disk with a r/2 as our new radius, and we have to find the relevant moment of inertia for this figure. Okay, the concept you really need to be aware is, well, obviously the moment of inertia, but also parallel axis theorem. It's like you can have any number of parallel axes that's perpendicular, that's parallel to the axis that goes through the center of mass, and there's a formula that illustrates it very nicely. So to solve this, I'm just gonna first write down the very key equation. I'll say the moment of inertia for this figure can be calculated by the full circle's moment of inertia, I full disk, minus the cutout region, cutout disk. Alright, so obviously the full disk was given by the formula, or some of you might memorize this, have memorized it already. So you want to just write 1/2 mr squared, and then we have minus, and based on the parallel axis theorem definition, we're gonna have the I, C, and the center of mass of our cutout region plus the mb squared. Okay, instead of bogging down to the derivation of this formula, I'm just going to illustrate this to solve this problem. So we have to find the right, correct mass that's relevant to the cutout disk and the distance. Alright, so I'm gonna first define the ICM here, the center of mass. Okay, obviously the center of mass of our cutout region is going to be center of this circle, and we before that we have to find the mass of this cutout region. So using the proportionality, because we have a similar figure, just like the similar triangles, it's the same shape, same thickness of the disk, therefore we can use the m, big M, as the mass of our full disk, and on top I can have area. So the area of this circle, or volume, okay, we can ignore volume because of the same thickness. So I can just simply have the area. The area becomes pi r squared, right? So you have pi r squared. Okay, for our cutout region, due to the similarity, let's say I want to find the x, the mass on the bottom, and then I'm gonna have on top the area of this white circle. So I have pi. Now we have r/2 as our radius, so you have to put the r/2 within the parentheses, and then you have to square that. So eventually you get the pi r squared over 4, and then x really becomes m over 4 to keep the equation correct. So in other words, when we have a mass of this disk, that cutout region becomes m over 4. So in our moment of inertia equation, because it still retains the shape of a disk, I'm going to simply plug it in m over 4 as our mass. But don't forget we have 1/2 that retains the full disk shape. And then, let me first finish this. I'm going to distribute the minus sign, and this mass is still pertaining to our cutout disk, so it takes up. Oh, I forgot the radius, right? So I have to put the r over 2 and then squared, and then m over 4, and we're gonna just set the parallel axis on the center, and it really doesn't matter anywhere, but any region along this circle we're gonna keep that, because that makes our calculation much easier. So the distance is gonna be from that to our center of mass of this cutout disk is again r over 2, and you also have to square that. And as you simplify our expression, you get 1/2 mr squared minus 2 times 4. Now watch out, you have a squared for our r over 2, so you get 4 on the bottom. So 4 times 4, 16 times 2, you get 32. And on the top you get mr squared. Over here we have 4 on the bottom times 4, you get 16, and then you get mr squared again. So we can have a common denominator as 32, and on top I'm gonna have 16 mr for the first term, and for the second term I have just simply minus mr squared. For our third term we have negative 2 mr squared. Okay, so 16 minus 1, 15, 15 minus 2, you get 13, and we are able to do that because mr squared are present in each term. So we have 13 mr squared over 32, and that's our final answer for the resulting moment of inertia.